second night talk of the Brain Awareness Week at the Erasmus University College. We are really happy to have you in our beautiful building. So for those who don't know, the Erasmus University College is the liberal arts and science of the Erasmus University Rotterdam. We are slightly isolated because it's an independent program, but we have a major in neuroscience, and that's why we are organizing the Brain Awareness Week. So the Brain Awareness Week is already, this year is the 30th year of the celebration. It started in the United States, and it takes place every year during the third week of March. And the idea is to connect people with those that do strange stuff and interesting stuff and important stuff to learn about the brain, to better understand human behavior, to see if we can improve our species a little bit by understanding how the brain relates with the human behavior, right? So because of that, me with a nice group of students that are not around, because they are students, of course, so we have organized a nice series of lectures. So on Monday, we were talking about the optical aids to for art perception, because the topic of this year of the Brain Awareness Week is brain and arts, right? So this is the second talk. We have Mario with a complex background, which I will briefly summarize in a moment, who would be talking about brain intelligence, well, human intelligence versus computer intelligence. Tomorrow, we have a very interesting activity, the Club Central, where we will have 4 neuroscientists with different backgrounds showing us 5. Yeah. I'm sorry, I put you already in there, man. 5 neuroscientists showing us their artistic skills in the context of storytelling, poetry, music, improvisation, juggling, you know? And then we will have a kind of talk how this is related or how this has helped them improve, I don't know what happens with their path in neuroscience. On Friday, in this room, we will have the former dean of the Erasmus University College, now is the dean of medicine, the Faculty of Medicine at the Erasmus Medical Center, Martin Friends, who will be talking about the Beatles and the brain. So don't let it be just like that. And we will be closing the activity on Saturday at the Natural Histories Museum, where we will have the Brain Lab from Sofia, so you can bring your kids, anyone you want to invite, walk around, experiment in the lab. We will have nice stands and inside the museum, short talks about different topics. And then you will also have the opportunity to join and visit some of the different neuroscience and neuropsychiatric labs at the Erasmus Medical Center. So please join us, but no more. So we have Mario Negrello, a friend of the house. He has a PhD in computational neuroscience, so he does PhD. He does computational neuroscience. He did the PhD in Germany, then he went for a postdoc in Japan, and he has been part of EUR, EMC for some period of time. I don't know how long.
Yes,
how long?
12 years now.
Oh man, 12 years. And we are working in some things together to bring our students from the whole community together. So thank you, Mario, for taking for being us. And thank you, please enjoy the talk. And yeah, all yours.
Thank you kindly. Thank you for having me. Thank you for having me. Always start, yeah. How to begin a talk? By welcoming the new participant. Allow me to just tell you that this is where I work. This is basically my day occupation in the neurocomputing lab in the Erasmus Medical Center. We study the brain, obviously, but with synthetic tools. So we do computational neuroscience in many different ways. We are actually mostly concerned with biophysically plausible versions, biophysically plausible models of the brain. It's interesting, like I'm generally not nervous for talks like this. It is a different setting, like it's very fresh building, very inspiring crowd. And I feel somehow that this has a, like in Portuguese, I'm originally Brazilian. In Portuguese, you say, I am prata da casa, I am the silver of the house. Like I'm basically worthless, just like, a friend of Anderson. He invited me here to talk about something fancy. Now, I want to share with you not so much what the fancy research that we do here at home, but I want to share with you what I think is a great way to think about the brain and to expand our minds in a way as to help us understand ourselves in the spirit of the Brain Awareness Week. So the talk that I made today is exclusively geared towards an outreach public, many of whom I already know because they have been in the minor, the computing brain that I organized, like about these types of topics. And I am so happy to see them all here. And without further ado, I'm just going to get on with it so that I don't give room for my emotional gaps to fill in. So the title that I decided to give the talk today is Peaks and Valleys of Memory. And since we're talking about art, we are going to talk about creativity, and I'm going to cast this in a particular frame, which I and others have christened before as an attractor landscape. Now, as you will see here and onward, the emphasis on the talk is going to be analogies and metaphors. Maybe some of you already realized that whenever we're thinking with pictures, we're making connections. And it does feel somehow, even if you're thinking about words, that you're connecting semantics, you're connecting the meaning of words, and dreaming is connections between dissociable concepts. But trains of thought are when you're concentratedly thinking about something that creates a chain of thought, like an element after an element and another element. So we're using analogies and metaphors, train of thought, for instance, to describe our own thinking to ourselves. This is basically the effort that a computational neuroscientist wants to invest himself in. So how will the metaphors help us explain the parts of the brain for ourselves? Because ultimately, we're only explaining this, we're doing this research, we're doing the science to explain it to ourselves, right? So we're humans, we want to understand the brains, this is a mirror, this is my science, and I'm going to try to reflect upon the ways in which I think so that I can cast the ways in which I think in the way that I'm built. The neurons that I have, like basically the Lego bricks that I know must be there. And so the lecture starts by saying that everything that I'm going to say today is basically an analogy. And even as we're using sophisticated modern models of computational neuroscience that in fact in 2024 got the Nobel Prize, these are only pictures that our mind uses to create some body, to give understanding. I actually will invite you also to later think about what is actually understanding, what does constitute understanding. And this lecture wouldn't have been possible without generative AI, because I've started it today by asking my dear friend ChatGPT in the prompt that I put upstairs, can you make a quote collection from thinkers that have said that we understand through analogies? Start with Hofstadter. Douglas Hofstadter, great thinker in cognitive science. This quote is actually correct. Analogy is the core of cognition. Cognition is our ability to think and make sense of the world. And that is actually a correct reference as well. Surfaces and essences, analogy as the fuel and fire of thinking. Now, I definitely invite you to read that essay. It's not very long. I fact-checked some of these references, and this is a cautionary tale for all of us that are using generative AI. Some of the quotes are only correct in spirit. Some of the quotes are partly correct, and this is Poincaré, one of the dynamical systems physicists who basically created many mental pictures that we now use to understand the brain. One of them, the attractor. So the attractor is a word that is going to come in this talk more than a few times. But
did actually say in this book, Science and Method, which is about education, and it's about pedagogics. It is by logic that we prove, but by intuition that we discover. But this is not right. This is not in the book. And intuition always consists of seeing analogies. So please, know also what not only the limits of the metaphors we use, but also the limits of the assistant tools that we have. But too much about this. I mean, just to create this embedding for our conversation today, there is analogies. We're going to talk about spatial temporal patterns. First and foremost, I would like to tell you that a spatial temporal pattern, oh, I see that I actually, there is a typo. Spatial temporal, not temporal. The point here being, we humans are interfaces to the universe, right? We have the skin and you can sit on a chair and that will create a certain pattern on your interface with the chair, which represents the weight that you have on it. Similarly, when you're seeing the pictures that you're receiving from me, you're activating your receptors, your retinal receptors in your retina, creating pictures one after the other, which represent this world. This is a pattern. This is a spatial temporal pattern. Similarly, the words that I produce come to you as waves and they start resonating your ears, and this resonation is converted into brain activity and eventually producing a percept, right? So you have physics, which is the world outside. You have us, the interface, with the many types of interfaces we have. They're different modalities, some people call them, or the senses more commonly for school. And then you have the percept, the qualia, the things that feel to us, the way that something would appear to us. So touch is different than an image. However, if I'm basically imprinting my hand on a three-dimensional or two-dimensional texture, that imprint on my hand can be actually a picture, right? I don't know if you can form this mental picture in your heads. If you have an embossing of a certain of a house, then you put it in your hand. Why can you not see it? These modalities are different, but there's a commonality. And the commonality is the representation. The fact that you can talk about anything that enters our perceptual system in terms of this general concept here of spatial temporal patterns. There's a video about that, and I would definitely recommend you see it. AI took over the world because everything is a pattern. And this is not my own persuasion, this is many people's persuasions. And I would like, if you haven't thought about the world as sequences of patterns before, this is the way that we're interfacing with it. Now, okay, so this is what in physics we call the boundary conditions, the stuff that is the way in which it imprints upon us. But if you've been to any other Brain Awareness Week talk, and in fact, I had planned to ask a little poll before, how many of you know how a neuron looks like? Raise proudly, right? I mean, like, how many of you do not know how a neuron looks like? Okay, there are pictures, like I should actually do I want to make I didn't really put a picture of a neuron here, but I can create a small little, I can create a small caricature of what a neuron looks like, and I would recommend just basically Google images of neurons, and there's so many, they're pretty. So this is a neuron, and this is a caricature of a neuron, and I guess that even if you hadn't seen many pictures of neurons in a microscope, like in a scientific form before, you did have the mental picture of something that receives information. And so this is generative AI. So generative AI's idea of what an information flow might look like. This is just a fancy picture, but the idea here is that you have a network, and in this network, activity flows. The neurons, one activate, the other one activates. You have a cascade of activations. Activity propagates. What is this activity about? Well, the activity is about what happens to enter through the interfaces. It is all clamped to the world. If you close your eyes right now, and you don't see the room, you don't see the room. The room is giving itself to you via this interface, and this interface is pushing that information through and creating these images for you while your eyes are open. Your eyes are closed, don't quite create the pictures the same way, potentially during dreams. But the point being, interfaces bring information in. And this information propagates. And propagation is another metaphor. It happens to be a representation of dominoes that knock each other in a sequence, and it happens to be the mental image that many researchers have already thought about. So this is propagation in a little demo made by a person called Nicky Case, and Nicky Case created this to give us the idea of how is it that new neurons are propagating. Is this a good picture? Oh yeah. Is it a complete picture? No. No, it's not a complete picture by any stretch of imagination. But in any case, this is where we're going with this. We're going to talk about not natural neurons first. I'm going to give you a simplification that convinces me. Also, even my biology brain is convinced by this simplification. So artificial neurons, they don't look like that. They look like circles. And the circles contain numbers. Which numbers? Which kind of numbers? Well, make them simple. Make them numbers that go between 0 and 1. And maybe make these numbers, they kind of represent a quantity, more than an exact number with infinitely many decimals. What these numbers represent is some amount. So it's either full or it is empty. It is even firing at maximum firing rate, or it is not, ones or zeros. Now this is the metaphor of artificial intelligence today, and this is what we call, it's basically a weighted sum. It is an analogy to what the real biological neurons are doing. There's not summing like a calculator, but we, through this analogy, can believably impose it on ourselves that this is a theoretical, good theoretical way to think about. Particularly, so this is a typical artificial neural network, and it is summing the values. And what this neuron here in the bottom does, it decides if this value is good enough or big enough so that it will activate, right? So maybe 3 is more than 1, and so we're going to say that this neuron now is going to be activated. Accumulated all the activity and activated. Now, step number 2. When the types of networks that we're going to be discussing today are association networks. They won the Nobel Prize last year with the John Hopfield being the main one of the people that shared the prize. But we no longer call them Hopfield Networks. They're also called Hopfield Networks, but it turns out that Hopfield published in 1981, whereas Junichi Amari had published the same work in 1972 in Japan. And so he wasn't recognized by the Nobel Prize, but never get bogged with the details. The types of networks that they were thinking about were not like this one, in which you have a collection, a feed forward, a directional collection of this activity. The networks that they were thinking about were actually like the brain in the sense that they were all connected. And this is a picture that many people that go into neuroscience start with. People tell the neurons are connected everywhere to, all neurons are connected to each other. That's unlikely. There's a lot of anatomy in the brain, and there's specific activities, but as a first approximation, this works. Not only, but also when we through a second process, these neurons, as I give them to you here, they can be arranged in different patterns, and this is going to become important in a moment from now. The point of association networks is also due to one of the fundamental insights, not only in computational neuroscience, but in neuroscience in general, by a guy called Donald Hebb. And what Donald Hebb said, which is not exactly what I will say, I will paraphrase. What Donald Hebb said is that neurons that fire together, wire together. Now, you may have heard this trope. And here, I can make two neurons connect by creating a certain sequence of these connections. And basically now I can activate the network and see where this information is going to be propagated to. And again, an incomplete picture, but a valid picture to a first approximation. And so, interestingly, if you do this, if you create a network that has recurrent connections, recurrent is the word that we use to talk about the fact that this neuron is connected to this one, but this one is also connected to that one. So basically, they're symmetrical. They create association. Think about a pattern entering in your retina. Now make it much simpler. Make it black and white. And maybe you can see here in the black and white that there are activated photoreceptors in your retina by +1 and deactivated photoreceptors in your retina that have a -1. Created this animation in the morning, so it's not like thank you to 3 Blue and Brown and ChatGPT. One prompt created this animation. In any case, here the point is the pixels in your retina that form the spatial temporal pattern of these images coming through you, they have some sort of structure. Some people would call them statistical regularities. Some people will call them patterns, but they're structure. And this structure is, through Hebbian learning, a way in which the brain can wire. And the beauty is, just with these two small assumptions, you can construct what is called an attractor network. Now I'm going to change gears into something very fun. So this is, I think I can click. I had created this, so let's see. Yeah, takes me to Safari, but not to the right place. It's a little demo online that you can play with. This is a Hopfield network, and here you have the bits. And each of this you have to think about being a neuron, okay? And maybe it's a neuron in your occipital cortex, like a visual neuron. And it's connected to all of the other neurons in your visual cortex in particular ways. However, when you see a bunny, the pixels participating in the bunny, they are wired together because that statistical regularity keeps on happening. So this is a pattern that is there, present. Can have other patterns. And these patterns are things you learned about, right? So they're things you see in the world, like aliens you see all the time in the world. In the background, you have noise. The world is not always the same, and the way in which the patterns imprint on our brains change. And so sometimes what you see is not exactly what you've learned, but something that is similar to that and incomplete. In this Hopfield network, I have created an initial state that represents a noisy version of this alien. And when I tell the network to compute, and what does it mean, the network to compute? I just showed you, is basically the network is summing the input. Every single node, every single one of these pixels here is a neuron, and he is summing inputs from all of the neurons. They're connected. I'll show the picture in a moment again. Maybe it will make more sense. When I say here settle, I basically am saying, start from this pattern. Given the connections that you had learned, what are you thinking about? Oh, that's what I'm thinking about. So a Hopfield network will go back to what it had learned, right? So it had learned this pattern, and even if I create a very noisy pattern, and then I settle, you will remember that. So it will basically see that pattern again, because you had been taught that pattern now, saw it in the world, is imprinted in you, you will remember it. This is an attractor. dear participants, dear attendants. Attractor, dear attendants. The idea here is that recurrent neural networks store information in terms of patterns with in their connections, such that the letting them run will basically collect the state to a minimum of energy. This is another metaphor that people in computational neuroscience work on quite often. The idea that you're going down some sort of mountain, and this mountain is all the things you can be thinking about. Given that input, you're gonna actually converge onto this. Now, clearly, this is a toy example. We always talk about these as toy models, right? Like they are giving us mental pictures. But this little toy model has enormous explanatory power. And this is why I'm actually telling you about this. So if you're more curious about this, Jack Terwilliger, candidate, PhD student, wrote a lovely little explainer about it. Now, in this explainer, he will use the metaphor of an attractor landscape a few times. You see here, what you see in this sheet is that these are, every point here is a place your brain can be. But because there is some sort of rugosity, some sort of structure into this landscape, when you start in a particular place, you land in a different place. Maybe this is not a great picture. Waddington was talking about the epigenetic landscape when he used the same metaphor. If you see time as progressing in this direction and the ball being a representation of where your brain is, and this is actually a good representation, even though super simplified, it will roll down the hill in particular ways. And you will see that sometimes you will, not know where exactly you will roll down to. So there is a bit of a critical moment. Here you will have to make a decision. And the decision is a bit random and chaotic. And you don't know. We actually use the word critical to explain these types of state divergences here. And so the attractor landscape here, for instance, help us explain things like bistability in perception. And bistability is the idea that you can see from one picture two things or even more, in which case we actually talk about multiple stability. What do you see here? Saxophone or lady? At the same time? Yes. At the exact same time? That's good. How about this one? Vase or two faces? At the exact same time? Bunny or duck? Exact same time? Can you see the bunny? So it takes a while. It took me a while to see the bunny, but then eventually I did. The bunny is looking at the different opposite side. So this is a little perturbation that is taking you from one attractor that brings your perception to one mindset, to one semantic value. You interpreted this. You not only saw the pattern that went into duck, but you have a word now, duck. It's either a ceiling or it is a staircase in different directions. 2022, a paper I found today, a series of unforced events using the same metaphor to talk about this attractor landscape idea. The fact that because the network has a specific structure, it has places it can go, right? It's not like your brains are random. Your brains have places where they can go. And in fact, that sometimes it's all the same places over and over because we are cyclic people too. We're kind of like periodic in our minds. And if you look into the brains and you measure activity, you will see that these activity patterns in the brain also correlate with the things you're thinking about. Another cool example of things that these networks help explain is pareidolia. The ability of seeing, for instance, a face in a key, in a handle, or seeing like a brain in a cloud, or seeing animals in clouds. So this ability is like, okay, you've started, you're looking at a pattern that is not quite what you've learned. But given that initial condition, you're kind of flowing into a mental state that collects that picture. But clearly you're not having a, we humans, we're not so single-minded. We're not toy models of ourselves. We're complex models. And so our attractor set, like the number of attractors we can have, is enormous. And not only is it enormous, but they're completely connected. So you have a bunch of, in a sense, you have a bunch of different networks in your brain. Your conscious stream is going to collect all of these attractors into one thing that you're perceiving now. We're also kind of narrow. You cannot do all parallel. We're basically experiencing a flow of time, and things seem to happen in a sequence, even though they're complex. And so the brain does not have a single state in the attractor landscape. The brain is not a single bubble that is going into like the possible attractors. It is actually a bunch of bubbles, and they are going in from one ridge to another valley, and they are basically exploring the rugosity of your connections to create associations and to create connections that represent, for instance, between other things, creativity. Right, so you're going from one concept to another concept. You went from the bunny to the alien and maybe to something else. So when we're creating associations, the idea is that it's not just like a Hopfield network that produces one end state that is like a frozen picture, but it's more of a dynamic picture creation device that is both interpreting the world sequentially, but also if you close your eyes and you're in a calm state, or you give it some space of thought, you will transition from state to state, creating brain associations and trains of thought. Great job by Sora here. So I've described this as being, I want a locomotive in the shape of a brain, bringing a bunch of wagons in the shape of neurons. But that's not exactly what OpenAI managed to do. Now, admittedly, this is a relatively mechanistic view of the mind, right? So now I'm telling you that parts of creativity are built upon recognition of physical patterns that impinge upon us, like, for instance, a word. A word, what is a word? A word is a set of air oscillations that vibrate my inner ear in a certain way and produce certain frequencies inside, and that word gets interpreted as word. Notice, most people, if being told word, will interpret word as being a word, right? So you have an attractor for this particular inference. And I mean, we're not going to talk about ChatGPT just now, because the idea that I had is for us to have a nice discussion after this primer. So first we're going to be having this chat, and then we're going to open for discussion. So this mechanistic view of the mind is something that you might be bothered by, right? Because we don't like to see ourselves as machines. We like to see ourselves as experiencing the universe and the world. And so the attractor in this metaphor is just one picture I'm giving you. It doesn't explain what we are. But that's not what I'm trying to do. What I was trying to say is that what you're going for is an analogy that helps you think about how you think. An analogy that has the right mechanisms that are compatible. I mean, in mathematics, we often use the word isomorphic to represent these ideas, things that look the same in some sort of structural way. So by lifting detail from the brain, we are able to create a model that gives a simplified picture that allows us to understand. And what does understand mean? It means that you feel like you can reconstruct that in your brain somehow, that it's justified belief you have. And so attractors and attractor landscapes have enormous explanatory power. They are not the whole story, but with respect to creativity and memory, they give us a lot to work with. And these ideas in different levels of complexity have been used to talk about the free association in brains, right? Go from one concept to another idea, or in trains of thought, as I mentioned, in dreams, but also biases, right? So you experience the world in a certain way, and therefore you have biases. Biases are inherent to how brains learn. And Hopfield Networks give us a way to think about how we are biased by data. It also explains how you might potentially create new connections. When we were talking about the landscape with the decision point, right? So there's a ball and the ball doesn't know if it's going to go left or right. That might actually, you might have never gone right up until that moment. So within slightly different context, you might veer off towards a novel place in your brain. And in a sense, it also gives us things to talk about, because with respect to mental space, a network that works like this, can never not do what it's trained to do. Its activity, it's always going to go to that place and stay. If the brains work like that, you could never have silence in your hearts, right? The brain works a little bit like that, in which we mostly don't have any silence in our hearts, but we can achieve silence in our hearts as well. And that means basically we can also stop, we can, by breathing, find ways of putting some milestones in that process. And this metaphor of Hopfield Networks is also part of what nowadays embodies like our training of generative AI. So the idea is that we, by seeing things that we already saw in the world, descriptions of pictures that we have, we give this back to the computer, these patterns that we see as humans, we give it back to the computer and train them. And so there is this, when I wrote this prompt, I actually wanted the information to flow from the computer to the brain, but alas, it's better used for this metaphor now. We also train the computers to become a little bit like us, but when we train them, we don't only train generative AI, we also train each other, right? So we're giving each other patterns, and these ideas that we share basically are these information flows that supervene on the brain. If this stuff seems like, admittedly, incredibly superficial, very shallow, the talk that I gave is to excite you to pursue potentially an interesting venue of explanation of brain. And there's a lot of cool stuff out there that will give you a bit more detail about any of these ideas. But you might already have stumbled upon Kurz gesagt and up there, 3 blue, 1 brown, if you really want to understand how networks are. We have a YouTube channel as well. It's called The Computing Brain. It's where we put some of the material for the course, the AI minor we have. And the way in which I wanted to get a segue for discussion now is to thinking about the limits of metaphors. I mean, I'm sure that as you were listening to me, I mean, we are naturally skeptical as humans. We have like many reflexes that we don't like some stuff, or make stuff, it's missing, big stuff missing from the picture. Let's talk about that now. Let's see where else can we go. So the reason why I put the last one there, a plane is flying, a submarine is swimming, but is a computer thinking, is I think an interesting question to pursue. I did add here some information like about absolutely foundational readings in this topic. I don't know if we would ever make the slides available, but the talk is recorded, is going to be in the Computing Brain channel. So if you later want to check out what are the references that we're talking about, you'll find it there. And last but not least, so the minor is cool. Is the minor cool? So for third-year bachelors, you might know someone that is searching for a minor and might have these types of pensions. We have a minor that runs between September and November from the Erasmus Medical Center, where we unpack a lot of these metaphors, and we do this systematically, also looking into the neuroscience data. Here is an outreach talk. I just wanted to give you pictures.